Hey there everyone, all the techies and data enthusiasts there. So guys, welcome back to my YouTube channel. This is video 5 of our transformer series, and in this particular video we are going to discuss about residual connection and next step after feed forward neural network. What will be our next process? About them we are going to discuss in detail. So guys, in our previous video we have already discussed about self-attention mechanism and multi-head attention as well. It is a very interesting video and those concepts are very important. If you have not referred that particular video, do check out the video link is in this video description, and once you understand that video you will be able to understand this in detail. So if you have not subscribed the channel, do subscribe the channel and on the bell notification and support me to create more videos like this, and do follow me on LinkedIn. So guys, now let's get started. So guys, if you see the summary of our previous book, we have already discussed about what is QKV, which is nothing but query, key and vectors, value vectors, and analyzing the outputs of self-attention and multi-head attention with code. We have checked that. So now today we are going to discuss about residual connection, in which we get adds and norms, which is nothing but the crucial part where each layer in transformers encoder architecture. It consists of mainly two components: a residual connection add layer and a layer normalization, which is normalization layer. The combination enhances the training of deep neural network, making more efficient and effective. It means that, see, once we have done with attention mechanism, those outputs will be sent to our residual connection and layer normalization process, where using this we will normalize the layers and bring the neural networks to be more effective and meaningful answers out. Okay. So the purpose of adds and norm. First, we'll discuss about residual connection. A residual connection allows the output of a layer to be added back to the input. In simpler term, it means that the original input is preserved and combined with the processed output of the layers. Means whatever output we get, right, we just add back them to get a better, more results. Why is it important? And one more thing, see, the original output will be still preserved. Only the part of it again will be added back to get better results. If that comes better, it will consider that. So, information retention. By adding the original input to the output, the model retains important information that may otherwise be lost during the processing. This is especially crucial in deep neural networks where layers can distort the original signal. So this is mainly important where there is a high chance of layers getting distorted. In instance, connections might be failed and there is more chance of vanishing gradients or loss of data. Learning identity functions. The residual connection allows the model to learn and identify functions in a deeper layer. Do not improve performance. They can also effectively pass through the unchanged input. This is beneficial for avoiding the vanishing gradient problems, as I told you already. And layer normalization. Layer normalization is a technique that normalizes the output of the layer across the features for each input. It adjusts the mean and variance of the output to ensure consistency, to ensure the proper stabilized training, right? So we normalize the layers and bring it with a proper accurate connections to be better processing or to work better. Why is it important? To stabilizing the training. So that is one thing. And fast convergence. By stabilizing the output, layer normalization allows the model to converge faster. It can learn more quickly and efficiently, and even there is a high chance that it will be more accurate, whatever answers we get. How add and norms works, or else in short you can say residual and layer normalization works. After multi-head self-attention, the output from the self-attention layer is combined with the original input using a residual connection. This means that you add the original input to the output of the self-attention mechanism and then combine the result to pass the layer normalization and stabilize the output. So here you can see here in detail. So this is a formula: output attention is equals to layer normalization, input attention plus self-attention of X. Okay. So output 1, input word and output 1, 2, 3, 4, 5. These all are sent to residual connection, and residual connection will send it back to attended output 1, 2, 3, 4, 5, and they are again normalized and they are sent again. Layer normalization is done. After that we get normalized output 1, 2, 3, 4, 5. After feed forward network process, Similarly, the output from the feed-forward network is combined with the output of the previously add and normalization steps using another residual connection. Normalization, this result is again passed through the layer. So the normalized output which we have, right? Again, we send that to feed-forward network, and feed-forward network output again we get, and we process it. Yeah, we process it and we get the final feed forward normalized layer normalized output. Okay, in short, here two times the things goes on. So once we get the output right from our self attention, we send that to our first add, which is nothing but residual connection. So let me explain here itself. So whatever outputs we get, right, we send that first to residual connection. Then the residual connection attends the output, and the whatever output we get from residual connection, again that we send to layer normalization, and then layer normalization give us a normalized output. So until here, that is one process. Once we get the normalized output, again we give it to feed forward neural network. You can say kind of like ANNs, RNNs, CNNs, which we are having, right? Neural networks. So there is a feed forward neural network which we provide to that, and from there you again get a feed forward outputs. Whatever outputs you get from the neural network, that again you send to residual connection, and residual connection normalize and sends feed forward normalized output. So two times process this is, you can say. So here you get, after doing all this process, you get more stabilized answer. So feed forward neural network is a type of ANN. So I told you that it's a type of ANN where the connection between nodes do not form cycles. Information flow is in one direction from the input layer through the hidden layer and finally the output layer without looping back. So there is no loop back. That is the main reason we again normalize the thing. So you can see here, for better understanding, feed forward network is also explained here. So input layers x1, 2, 3, 4, and we have the weighted sum, which is, this is the formula for a neuron, w1 x1, w2 x2, and w3 so on. So weight and bias will be there. So this data whatever we have, we first send to weight, and we have a bias as well. Then there is a formula wj plus xi, sigma of wj plus xi. This is the weighted sum average formula to get the sum. This is nothing but a hidden layer which performs all these things. And after that, we finally add a activation function called ReLU activation function or sigmoid activation function. So there is formula of it. You have ReLU and sigmoid and tan. Any of this activation function can be used according to your requirement. Finally, we get the output. So after, in short, in ANN, what it happens is input, then layer normalization, or you can say that a weighted bias normalization will be there. And after this, you add a activation function, and after that, you get the output after doing all these calculations. So here the complete diagram is here. If you want, you can have a screenshot of it. This is a very clear diagram to say of AN, and I guess no one else have created like this. Very clear and very simplified version. So applications of feed forward neural network. So image classification for image classification, for natural language processing, for regression task and pattern recognition. In short, this feed forward neural network which you are seeing, right, ANN, this is the base. If you understand ANN properly, you will easily understand RNNs, CNNs and their submodels. Like you have LSTM, GRU, and in CNNs you have AlexNet, LayNet, VGG16 and many other sub-process, or you can say sub-models as well. You will understand them very detailed. Once you understand them, in short, your deep learning starts with ANN only. So if you understand this very well, then after that you will get in transformers, and in GPT architectures you have in BERT architectures, encoders and decoders architectures, and even right now in LLMs also this is there. One part is there. So without knowing all this base, right, if you directly dive in, you will do it. But for deeper understanding, to work for research purpose, those who are going to see, right, data scientists, they definitely require this. In interviews, the first question will come, what is ANN, or explain feed forward neural network. There, if you don't explain this properly, you are directly rejected. Okay, so make sure to understand this very clearly. And after this, we have applications of feed forward network is done, and summary. Okay, so this is actually a very short thing. You can say in today's, there is no much coding. It's all about the practical explanation about ads, residual connection and layer normalization, and feed forward neural network, which is even more important to us also. And it's a short video, I guess, for today, but it's okay. That's very interesting. So next video we are going to cover about encoders in transformer architecture. Wow. So it's gonna be very interesting. So guys, that's all for today's video. Do like, share and subscribe the channel. Meet you all in the next video. Okay, bye bye.